In this series of videos, I'm going to start talking about how to solve dynamic programming problems. And in this first video, we're just going to do a high-level overview. And then in later videos, we'll be doing actual implementations of code, and we'll be taking on harder and harder problems. And so I think a good place to start when talking about how to solve these types of problems is to look at what I think of as the most simple, or one of the most simple dynamic programming problems, which is the question of how many ways are there to reach the top of a flight of steps if from each step we can only take one or two steps? And when you first come across a problem like this, I think the natural inclination is to kind of think of yourself at the bottom and come up with some method of reaching the top, reaching the nth step. And so maybe you can have like a recursive function that takes one or two steps, or maybe you could do it iteratively with like a stack or a queue. But either way, we're basically going to be visiting every possible path up the thing. And when we reach the top, maybe we'll increment some type of counter. And this type of solution that kind of visits every possible path is called a brute force solution. And you really want to avoid that because it's going to have exponential running time, which basically means at each step we're going to be branching off to the n+1 and n+2 steps. And anytime you have this kind of branching factor, you're going to be building like a giant tree of function calls. And when you do that with large inputs, it's basically just not going to complete in time. And so what you want to do instead is, instead of imagining yourself at the bottom of the steps and having to reach the top, you kind of think through the problem backwards. And so you ask yourself, if we're at this top step, how could we possibly have reached this top step? And the answer is we either came from one step prior or two steps prior. And the thing is, if we know the solution to these two problems, the number of ways to reach this step and the number of ways to reach this step, we can just add those together, and that's the answer to the problem. And so we can write this in a sort of mathematical way, where the solution to the nth step is the sum of the previous step and two steps prior. And in code, this would just be like a recursive function that makes two calls and then adds them together. And at this point, this is still a brute force solution. It would still take every possible path, but we can improve on that by caching. And so if we think of a tree here where each node is going to be the argument to a function call, you can see that we're going to have a lot of overlap in terms of which function arguments we're passing. And a key insight, I think, is that when you look at all these values and all these repeated values, you can see that we actually, to solve this problem, we actually only have to go down this leftmost branch. Because once we visit this node and we save the value, by the time we're up here, we already have this value saved, so we can just reuse it. And so we actually only have to go down this one this one branch. And when you have a solution like this, in code it's just going to look like a recursive function that makes two calls, but in addition to the base cases, which stop the recursion, you're also going to check in the cache, which kind of serves as like an additional base case to stop the recursion. And that way, we basically eliminate visiting this entire part of the tree, and we end up with a linear solution instead of an exponential solution. And I think that's basically like the easiest way to understand these types of problems. But then to go one step further is to think about what's called the bottom-up solutions, which are basically just, instead of thinking in terms of function calls, you're kind of focused entirely on the cache. Like in a sense, when you make the recursive top-down calls, you're building up a cache kind of, and then passing it as you go back up. And in a sense, like the immediate or the original function calls aren't needed if you start at the bottom of the cache. And so in the step example, we would have the two base cases down here already. And then we can just imagine ourselves building up the cache as we go, where we can kind of reuse the same understanding of the breakdown, but kind of thinking backwards. So instead of making a function call that then references these two values and goes all the way down, we kind of assume that we have these two values to begin with, and then add in the extra value to the cache, and we just keep doing that all the way up the steps. You'll see that we're adding in these Fibonacci numbers until we get the answer. And the thing with bottom-up solutions like this is it's kind of hard when if you only look at them without understanding kind of the top-down solution, or at least understanding how the sub-problems are used to create to find the solution to the actual problem. And so it can get kind of tricky, but I think the key really is to always think in terms of top-down and then kind of convert that to a bottom-up solution. And then eventually you'll sort of start thinking in terms of top-down, but you won't actually have to implement it. And another nice thing about this step problem is that in this problem it's actually literal steps, but you can kind of think about it in terms of logical steps too. And you'll see that there's a whole class of problems that are really just variations on this, where in this type of problem we're thinking about the two previous problems, but we might in some other problems be looking at all the previous steps that we've visited and maybe minimizing a value or maximizing a value. And then we can also do different things. So like maybe instead of the numbers at each step being like just an independent step, like maybe you'd have to pay cost at each step, and that'd be something you have to take into account. But the same basic framework could still be used for all these types of problems. And that can even be used for a more complicated problem, like if you could imagine a bunch of steps where instead of steps it's actually like values of a stock on some day, and the problem's like how do you maximize the amount of money you can make from buying and selling given like K transactions. Like you can still kind of use the same step metaphor where you're kind of looking back at previous days and building up a solution. It's just not quite as easy to see, but we're going to build up to that. I really do want to do that problem. That's probably going to be the last one in the series. And so, yeah, in the next video we're just going to actually code up this the step problem, and then from there I want to introduce also some more some higher dimension stuff. So instead of having a cache that's only a single array, we'll be doing sort of matrix type things, and maybe we'll do a graph problem too. And yeah, so stay tuned and check out the next video. I'm going to add I think I'm going to put all these videos into a playlist so you can find them easily.